Welcome to another video of this lecture series on Applied Physics UPH 004 course. In this series we are talking about thin film interference, and today we'll talk about wedge-shaped thin film. In this video we'll start with what is a wedge-shaped thin film, then we'll discuss how the interference happens in the case of a wedge-shaped thin film, then we'll derive some conditions for the maxima and the minima of the interference pattern, then we'll find an expression for the fringe width of the interference. At the very end, we'll find out what happens when we use a monochromatic light, what happens when we use a white light in the case of the wedge-shaped thin film interference. So here are some examples of such thin film interference that you see around. Here is a oil spill on a surface. The oil started to spread from around this central point, and then as it moved away from this central point, then its thickness gets reduced. So there is a change in the thickness of this oil film over the surface, and that is an example of a wedge-shaped thin film. So a film whose thickness changes gradually from one point to the another. And when white light is incident on such a thin film, it gets reflected and there are interference happening on the film. We'll discuss how that happens. And these white lights, after interference, creates this nice rainbow pattern on the oil film. Similarly, here is an example of a soap film which is held vertically and white light is incident on it, and you see again a nice pattern. So here, how is it a thin film in the form of a wedge? So when you put it in a vertical plane, then at the top the thickness becomes close to zero, but at the bottom it's maximum because of the gravity effect. Now as you are moving from the bottom to the top, there is a gradual change in its thickness, and that's why this is another example of a wedge-shaped thin film. And so on, you find several examples of such wedge-shaped thin film. So in one sentence, what is a wedge-shaped thin film? A film whose thickness changes gradually from one point to the another. So that would be the simplest definition of a wedge-shaped thin film. Now to describe how the interference happens in case of wedge-shaped thin film, let us first consider two different types of films. For example, one that is formed by one material. For example, here it's glass, here it's air. Glass enclosed by a top interface and a bottom interface, and these two interfaces meet at a point and gives you a wedge angle. Another type would be that there are, let's say, two glass plates. So here is one glass plate and this is held over another glass plate. So this is glass, this is also glass, and here is air, and this is wedge angle alpha. Now in this case, the film is formed by this material glass, and in this case the film is formed by air. So here is a denser medium, here is another denser medium. So two denser medium encloses a rare medium, and in this case here is a rarer medium, here is a rarer medium enclosing a denser medium. So that's how they are different. Now when we take the first type of the film, then the interface is right here, and when we take the second type of the film, the interface is here. Now let's try to understand how the interference happens. So a light ray comes and falls onto this. So this is our light ray. Then one part of it gets reflected from this interface, the first interface. Then another part gets transmitted, and the second part gets reflected from the lower interface. And after this reflection, it gets transmitted, and then when you look from here, you would see that this ray, let's call it ray 0, ray 1 and ray 2. These two rays, 1 and 2, would interfere and produce the interference pattern right on the edge. Similarly, in the second case, the light is falling, then it would come here, and then one part would get reflected from here, the first interface, and another part gets refracted first and then gets reflected from the second interface, and that's how it's going in this direction. So when you look from this side, you see interference pattern between ray 1 and 2. Now let us try to find out the conditions of maxima and minima. This is a little bit complicated, so to understand this, first we have to be very careful in drawing the required pictures. Let's say this is the wedge shaped thin film where the wedge angle is alpha, and that wedge is formed between the two interfaces OI and OI prime. And then a ray on the first interface, one part of it gets reflected, another part of it gets refracted, then this again gets reflected, then it gets transmitted. Let's give it some name, A, B, C, D. Now the incident angle is I and the refraction angle is R. Then this angle is R plus alpha. Then this angle is also R plus alpha. Now for these two rays, ray say 1 and 2, to form a interference pattern, the conditions would be related to the path difference between this ray 1 and 2. So how to find out the path difference between 1 and 2? So for this, we have to first draw a normal to the ray 1 from the point D. So this is normal and let's call it F. Then optical path difference is between 1 and 2 is, so the ray 1 and 2 get separated from this point B. Ray 2 travels from B to C, then C to D. During that time, the ray 1 travels from B to F. So the path difference is BC plus CD minus BF, but that must be multiplied by mu. Why? Because this is our medium with refractive index mu. So the thin film has a refractive index mu. So the optical path is mu into BC plus CD minus BF. Now we have to convert these distances BC, CD and BF into our known quantities. What are known quantities? First quantity known is the refractive index of the material, then the wedge angle alpha, then the thickness of the wedge shaped film, and let's call this distance B D. So this is the thickness of the wedge shaped film. So at this point, let us draw a perpendicular from point D to BC. So this is 90 degree. Now this angle would be R and then this angle would be I from the different properties of triangles. And let's give it a name. This point is, let's say, E. Now if we look at these two triangles BDF and triangle BED. So from this triangle, what we will have? Mu is equal to sine I by sine R. Snell's law. From triangle BFD, sine I would be BF divided by BD. BF divided by BD. And from triangle BED, BE divided by BD. From here you get BF by BE. So this would imply BF is equal to mu BE. So that's our first result. So we'll use this BF in here. Next we have to find out how much is BC plus CD. To do that, we have to be a little bit careful. So BC plus CD is equal to BE plus EC plus CD. Next, what we have to do is we have to extend this part of this figure from C such that these two lines meet. Let's call it point P. Also, if this angle is equal to R plus alpha. Similarly, this angle is R plus alpha. Now, BE, EC plus CP. So we wrote CD to CP. Why? Because from this triangle CDP, CP and CD are same because these two angles are same. Now next step, BE plus EC plus CP. So this part is equal to EP. This is equal to BE plus DP cos R plus alpha. So CD is equal to CP. This comes from triangle CDP. And this portion, that EP is equal to DP cos alpha, comes from EPD. Now let's go back here. We have mu into B plus DP cos r plus alpha minus mu be. From these two, we'll have this one and this one gets cancelled out, mu dp cos r plus alpha, which is nothing but mu 2d cos r plus alpha. So this is the first result. Path difference between ray 1 and 2 is mu 2d cos r plus alpha. But this is not all. Next, we have to consider two more things. From Stokes relations, we have looked at this couple of videos ago. Here is our thin film. This is a medium with a refractive index mu, denser medium. This is air and this is air. Let's say this is the first interface, this is the second interface. Then ray, when falls on the first interface, one part of it gets reflected. Then the next, ray number 1, ray number 2. Now, from the incident ray, when ray 1 gets reflected, then there is a phase difference between ray 1 and 2, and that phase difference is pi. And when the ray 2 gets reflected from the interface 2, then here there is no phase difference. So zero phase difference. So at the point A, the reflection includes a phase difference of pi. At point B, there is no phase difference between the incident and the reflected ray. So phase difference is 0. Correspondingly, so now in total, so finally phase difference is pi between 1 and 2. So this phase difference is nothing but equal to a path difference of lambda by 2. So now what we are saying is that between the ray 1 and 2, there is a path difference of mu 2d cos r alpha and lambda by 2. So the total path difference to mu d cos r plus alpha plus lambda by 2. So this is the path difference between the two reflected rays. Now these two rays, as they interfere, they will produce either maxima or minima. So the condition for maxima would be that this path difference is equal to n lambda, where n is 1, 2, 3 and so forth. Rearranging this, you get a condition of the maxima as 2n minus 1 lambda by 2. Condition for interference minima would be the path difference to mu t cos r plus alpha plus lambda by 2 is equal to 2n plus 1 lambda by odd multiple of lambda by 2. This is the condition for the minima, where n is 0, 1, 2 and so forth. Then rearranging this, you get 2 mu d cos r plus alpha is equal to n lambda. So these are the two conditions that we have to remember for the wedge-shaped thin film interference. So next we will look at the fringe width. Now to understand the fringe width, we look at a wedge-shaped thin film like this. So let's say this is our wedge-shaped thin film, and the thickness at AB is 0 and thickness at the edge CD is the maximum. So this is the thickness at CD. The wedge angle is alpha. What would happen if a light falls onto this surface? Again, taking a simpler picture of this wedge-shaped thin film, here is the point B, which is here, then D is here, and E is from this term. Now when light falls on it, with a wavelength lambda, at this point, let's say the thickness is D1. At this point, let's say the thickness is D2. Then with this D1, so similarly, at every point over this surface, the thickness is different. So some of these thicknesses may follow the condition for the minima, or some of these distances may follow the condition for the maxima. Whether a maxima of the interference will be observed at particular D would depend upon only if the D is satisfying the condition for maxima or condition for minima. So let's say this D1 is here and this is our D. If this D1 follows a minima, then along this line there will be a minima, because along this line at every point the thickness is same as D1. And let's say this D2 satisfies the condition of maxima, then there will be a maxima along this direction. So at different point over the surface, parallel to AB, there will be patches of maxima and minima alternatively. So when we talk about fringe width, basically we mean how much is the distance between two consecutive either dark band or two consecutive bright band. Now to derive the expression for the fringe width, let's say nth dark fringe was formed at this position, the distance of xn from this origin. Let's say this edge corner is the origin, and at this point the n plus 1th dark fringe was formed at a distance xn plus 1. Now fringe width would be distance between consecutive two either dark fringes or the bright fringes, so xn minus 1 minus xn. So this distance is the fringe width. How much is this? So if now you look at this triangle, let's say A, B and C, and if this edge angle is alpha, then this angle is again alpha. From triangle ABC, tan alpha is equal to CB by AB. Now let's say this distance is dn, so this height of this, the thickness of this wedge at the point A is dn, and the thickness of the wedge at the point C is dn plus 1. Then CV is equal to dn plus 1 minus dn. AB is equal to xn plus 1 minus xn. So the fringe width, let's say it's beta, is equal to dn plus 1 minus dn divided by tan alpha. Now how much is dn plus 1 minus dn? That you can calculate from this condition for the maxima. So at these 2 points A and C, we said the minimas or the dark fringes are there. So at A, the condition is 2 mu dn cos r plus alpha is equal to n lambda. And at point C, the condition is 2 mu dn plus 1 cos r plus alpha is equal to n plus 1 lambda. Now taking the difference between these two, we would have dn plus 1 minus dn is equal to lambda by 2 mu cos r plus alpha. So finally from here fringe width beta is equal to lambda by 2 mu cos r plus alpha tan alpha. So now by this time, if we have forgotten what was r was the refraction angle, and that can be calculated from the incident angle. Now from here we can have two special cases. If the light falls normally perpendicular to the top interface, then this would imply r is equal to 0. So beta is equal to lambda 2 mu cos alpha tan alpha, which is equal to lambda by 2 mu sin alpha. Second special case would be if the wedge is very sharp, that is alpha very small. This would imply sin alpha must be very close to alpha. So our second special case, beta is equal to lambda 2 mu alpha. Final case, what happens if white light is used? What happens when white light is used or incident on the wedge-shaped thin film? Single color or wavelength, then you see alternative dark and bright fringes of the same color. So let's say if you used only blue light, then you will see dark fringe, then blue fringe, then dark fringe, then blue fringe, then dark, and so forth. Then next, if you have used white color, means next if you used white light or multiple wavelengths, so lambda range of values. So in that case, what would happen? So you have the wedge and lights of different colors are incident on the surface. What would happen? So you have, let's say you are looking at the bright fringes. The condition is 2 mu d cos r plus alpha is equal to 2n minus 1 lambda by 2. So here there are several variables that you have to think about. So for a given incident light, r is fixed. For a wedge, alpha is fixed. Mu, the refractive index of this thin film, is fixed. Then what are changing? This d and this wavelength. So at every d value, So here is a D value, here is another D value, here is another D value. Several, let's say A, B, C, D. These are the various different points, and at every point we have the thickness of the film is different. However, at every point different wavelengths are falling. So for a particular point A with given the thickness, it may happen that one wavelength, let's say red, forms a bright fringe. So at all the points along this direction of A over the thin film, so here all the points would be red. Similarly, at the point B, given the width, it may so happen that the blue color forms a bright fringe. So you will have blue color here. Then at the point C, you may have, given the thickness, the pink color forms a bright fringe. So that's what will happen if you use a white color for the interference. You will have alternative bright and dark, but those bright fringes would be of different colors throughout the surface of the thin film. And this is what is shown at the very beginning on this slide. So here at different point you have different colors because the thickness is different and so forth. So with this we end this part of this lecture. Thank you very much.